Well, thank you all for coming out this evening. My name is Stephanie Edwards. I'm from Hope College in Holland, Michigan, and I'm here representing Pi Mu Epsilon, the National Mathematics Honorary Society, and want to tell you a little bit about our speaker today. Edray Herbert Goins grew up in South Los Angeles, California. The product of Los Angeles Unified Public School System, Goins attended the California Institute of Technology, where he majored in math and physics, and earned his doctorate in mathematics from Stanford University. He's worked as a researcher at both Harvard and the National Security Agency, and has taught at both Caltech and Purdue University. It was while he was at Purdue that I first met Professor Goins. He was supervising research for SUMSRE, Summer Undergraduate Mathematical Sciences Research Institute at Miami University in Oxford, Ohio. I had given a talk for the students, and as was the custom, the students and faculty took me out to dinner. It was a bright and eclectic spot. I can't quite remember the name of the restaurant, but I do remember they had paper covering the table. Well, being the insightful mathematician that he is, Professor Goins asked me a question about the functions in my talk. One thing led to another, and eventually we had the table covered with equations. The students had always heard about their math professor solving problems while they were uptown. Uptown is the place in Oxford where all the bars are at Miami. But they never thought it really happened. They thought we were just joking about it. Well, we proved them wrong. We solved some things. This commitment to working with students and his inquisitive nature are just some of the things that make Professor Goins an amazing and impactful person. His dedication to undergraduates was emphasized when he moved from a tenured full professor position at Purdue University to a full professor position at Pomona College in Claremont, California. He's written a thoughtful account of the reasons behind his choices in a retired AMS blog that's still available on the internet. When we think of Edray Goins, a word that comes to mind is impact. As a PhD student, he made an impact on his Stanford advisor, Dan Bump, who relates this story. Before tackling his thesis problem, Edray made a deep study of Felix Klein's monograph on the icosahedron. I was a little concerned about the amount of time this digression was taking. One day, he walked into my office, and I think I mentioned I'd not seen him for a while. He said, jokingly as I soon learned, that he'd been taking it easy. And then he showed me calculations of a new elliptic curve related to Joe Bueller's modular form. I realized then that he had done something remarkable. I was privileged to have Edray Goins as my student, and I am very proud of what he has accomplished in his career. Professor Goins has since made an impact in numerous mathematical fields, publishing research in areas such as applied mathematics, graph theory, number theory, and representation theory, and on topics such as Diophantine equations, elliptic curves, and African Americans in mathematics. When Goins was recently a visiting scholar at Harvard University, he made an impact on Richard Taylor of Taylor-Wilde's fame, who said, "Goins impressed me because he is very determined and really thought for himself, which is a rarer quality than you might think." But beyond Goins' mathematical accomplishments, he has made an invaluable personal impact on mathematicians of color at all levels, inspiring students at all stages, junior researchers and tenured faculty. As mentioned before, he worked at SUMSRE at Miami University, and he now runs a federally funded research experience for undergraduates titled Pomona Research in Mathematics Experience, or PRIME. Both programs prioritize students of color. He made an impact nationwide in February of 2019 when the New York Times published the article describing his experiences. For a Black mathematician, what it's like to be the only one. Along with his research and service activities, he was elected president of the National Association of Mathematicians from 2015 to 2020. Throughout his career, he has worked tirelessly to give Black students a chance to thrive, and we are grateful to him for helping expose many inequities in the mathematical culture. Now, we have 2 items of business to do before we enjoy Professor Goins' talk, which is titled, Distance Makes the Math Grow Deeper, Rational Sets, Nate Dean, and Me. The first is to point out that Dr. Goins is the first frame lecturer to reference another frame lecturer in the lecture title. Okay, the first frame lecturer to reference another frame lecturer in the lecture title. Yes, in 2010, Nathaniel Dean was the J. Sutherland frame lecturer for Pi Mu Epsilon. So, yeah, that's pretty neat. The second is to induct our speaker into my home Pi Mu Epsilon chapter, Michigan Delta, which is at Hope College. Pi Mu Epsilon's main objective is to promote activities that enhance the mathematical and scholarly development of its members. And in order to become a member, we will get to say the pledge. Now, I would ask people, if they are so comfortable, to rise as we can pledge and reaffirm our commitment to students and mathematics. So, are we ready? Special students, let's stand up. Pi Mu Epsilon, we're reaffirming it. Okay, let's go. We're reaffirming our commitment. So please repeat after me. I solemnly promise that I will exert my best efforts to promote true scholarship, particularly in mathematics, and that I will support the objectives of Pi Mu Epsilon. Oh, congratulations. And so here is your certificate.
Thank you.
Oh, sure. Sorry about that. Okay, so now please join me in welcoming Michigan Delta's newest member and the Pi Mu Epsilon's 2023 J. Sutherland Frame Lecturer, Edray Goins, who will speak to us about how distance makes the math grow deeper. Rational distance sets, Nate Dean, and me.
That was great. Thank you. Right. Wow, Stephanie, that was an amazing introduction, so thank you very much. I'll be the first to say, I never really know how my advisor thinks about me, so actually he said really nice words. That's really inspiring. Let me maybe say the first time I learned about Pi Mu Epsilon, I actually was invited to give a talk at the Pi Mu Epsilon induction ceremony in Evansville, Indiana. It was actually at the University of Evansville. Talitha Washington, who's the incoming AWM president, actually invited me to go there. And I had no idea what Pi Mu Epsilon was, and I was really impressed with the organization. I was impressed with the induction ceremony. So I do hope that those of you who aren't members of Pi Mu Epsilon, that you will consider being a part of the organization. What I'd like to do today is tell you some stories about a friend of mine who passed away 2 years ago. It was mentioned that I was president of the National Association of Mathematicians. When I became president in 2015, I took over from the individual that you see here on the screen, Nate Dean. He was the president right before me. I'd actually emailed him a couple of times just to kind of see how he was doing. We used to chat over LinkedIn. And then one day, out of the blue, someone sent me an email saying he had passed away several months before. In fact, I think that there's probably some of you in the audience who didn't even know until today. Some of you who had known Nate Dean probably didn't even know until now that he had passed away. It was very, very sudden. Nate Dean was one of these people where he just was full of life. He was a fascinating person to talk to. One of my favorite memories of Nate Dean actually was from the joint math meetings when it was in San Francisco several years ago. You'll notice here on the screen that his birthday is January 9th, so actually his birthday would have been next week. And so as part of the JMM, we would oftentimes do something. It might be go to a bar, it might be hang out, it might be just to kind of tell stories. Well, there was one day where we decided to go see a movie. Yeah, I know when you're a JMM, you're not supposed to go out and have fun about things. But we decided that we wanted to go see this movie. It was actually called The Book of Eli with Denzel Washington. Great film if you haven't seen it so far. But Nate would tell us these crazy stories like he was a black belt, but he really wanted to test out being a black belt. And you can't really test out being a black belt on mathematicians. So he would say that what he would do is he would just find the worst looking city block he could, walk down it just hoping he would get into trouble. Now, he did say that it never really happened, he never really got into trouble, but we kind of believed him that, yeah, he was crazy enough that he would have actually done that. So, so we're watching this movie and he's telling us all these stories, and it was just always really great to hear from him and to hear about these stories. So I want to spend today and try to tell you a few more of these stories, but also kind of weave in some mathematics around it as well. And let me just say that kind of the philosophy that I have with today's talk is this cheesy phrase here: mathematics is the closest distance between two people. Now, let me maybe say a little bit behind who was Nate Dean, for those of you who haven't heard of him before. He received his bachelor's in mathematics and physics from Mississippi State University in 1978, his master's degree in applied mathematics from Northeastern in 1983, and then his PhD in mathematics from Vanderbilt in 1987. Upon his graduation, he went to Bell Labs, and there's been a lot of individuals who went to Bell Labs who had incredible mathematical activity. I saw Bill Massey here earlier, who's at Princeton University. He's one that came out of Bell Labs. There's a professor at the University of Michigan named Jeff Ligarius, who also came out of Bell Labs. They just had some remarkable mathematicians who proved some incredible results. So he was a part of that whole crew when he was there for about 11 years. Well, in 1998, he decided to go into academia, and so he left Bell Labs in New Jersey, and first he became an associate professor in the computational and applied mathematics departments at Rice University, where he took on PhD students. But after being there for 5 years, he then moved to a historically black college, Texas Southern University, where he became full professor and he was chair of the mathematics department. Not soon after, about 3 years later, he moved to Texas State University in San Marcos, and he was there for about 10 years, and then he retired in 2016. But he was also very active in the various professional societies in mathematics. He was an associate editor for Notices of the American Mathematical Society for about 5 years, from 2001 to 2006. He then served on the MAA Board of Governors as the representative for minority interests for about 2 years, 2005 to 2007. And he was chair of the Mathematical Sciences Research Institute's Human Resources Advisory Committee, the HRAC, for about 10 years, for about another 2 years, from 2005 to 2007. And as I mentioned before, he was also president of the National Association of Mathematicians, a group that I'll talk about more later, for about 10 years, from 2005 through 2015. I was really amazed to learn, after I was invited to give this talk here, that he gave the Pi Mu Epsilon frame lecture, as Stephanie said earlier, back about 12 years ago, when he talked about his research and this idea of incomprehensibility. There's a lot more information about Nate that you can look up online, but I think that this here hits all of the main points. One thing I haven't said here is that one of the first times I learned about him was actually from this documentary that came out on PBS. So I was kind of finishing grad school at this point. I didn't really know a lot about the larger mathematical community, but I had heard about this PBS series. It was a series of about 6 videos where they just talked about what does it mean to be a mathematician. And they had various mathematicians, maybe about 20 or so throughout the 6 videos. They just talked about their lives as a mathematician. Some people talked about the research. Some people talked about kind of what they liked about mathematics. I highly recommend that you watch this video here that features Nate. There's about an hour of maybe 6 different individuals for about 10 minutes each where they talk about things. And the really cool thing about Nate, when the video starts, is you see him doing a kata in the background. He's basically practicing to kind of show off that he has a black belt. I thought that was the coolest thing that, a lot of us as mathematicians, we're really kind of the nerdy types that maybe will be at the chalkboard kind of showing off some things, or we might be talking about our favorite equation, but no, Nate starts off this video by showing off the fact that he has a black belt. After that, he does, of course, talk about the mathematics. He actually did work in data science, and he was very interested in kind of using properties of combinatorics and graph theory and understanding things in data science. But it was really cool to kind of see him in this video. Now, let me point out that he wasn't just an individual that was in a video, somebody that you might not see. He was very much active in the mathematical community in a very forward-facing way. There's a conference known as the Conference for African Americans in the Mathematical Sciences, or CARMS. And I fondly remember Nate being involved with this conference for years and years. In fact, here's a couple of photos from when the conference was being held at the MSRI, Mathematical Sciences Research Institute. And these are basically a couple of pictures of when people were hanging out in downtown San Francisco. So it was kind of this idea that, yes, he was in this video, yes, he was kind of this larger-than-life individual, but he was always willing to kind of sit down and chat with you about things. And I have to admit, one of the things I loved about Nate was that he was always willing to give you an open math problem. He would just kind of pull you in by saying, here's a really cool idea, something that I thought of, or here's a cool fact that maybe you don't know about. So you could just sit with him for maybe you might think for 5 minutes, but you'd end up having like a 30-minute conversation about some really cool math idea. And I do want to talk about some of these ideas today. One idea in particular I want to talk about are what are called sphere of influence graphs. Now, I first heard about this when Nate was a faculty advisor for something called RUF, Research Experiences for Undergraduate Faculty. You know how there are these REUs where you as a student can work on doing research? Well, the American Institute of Mathematics in San Jose, California, now moving to Pasadena, they have this wonderful program where you as a faculty member can do research during the summer with other faculty members. So they call this the RUF. Well, here's a picture from about 13 years ago when Nate ran one of these groups. And a couple of friends of mine were here in this group, and they would tell me about the research that they were working on. So I want to tell you a little bit about the research project that they were doing and how this influenced my own research. Let me start with a rather simple mathematical definition. And I want to talk about the concept of a distance between 2 points. So simply put, if you have 2 points, call them P1 and P2, and in this case, I'm just going to represent these by these 2 black dots. I can draw a line segment from one to the other, that's the blue line segment here, and the length of this line segment is what I'm calling the distance. Now, of course, you can either think of that geometrically and saying that it's the length of this line segment, or you can write it mathematically in terms of the square root of x1 minus x2 squared plus y1 minus y2 squared. Well, using this, I want to write down a few definitions, and in particular, the definitions that I'm going to use here come from a computer scientist named Godfrey Toussaint. So almost 25 years ago, Toussaint was interested in the following concept. Let's start with the collection of n points in the plane. So think of those black dots, just kind of spaced out however you want. The first thing I want to do is ask, what's the distance to the nearest member? So I have all of these different dots. I'm going to fix one dot and then ask, what's the distance between all of them, but maybe what's the closest one to where I am? So I take a look at all distances, and I'll look at the minimum one. Once I have that minimum distance, I can then draw a circle of that distance as my radius, centered at the point that I care about. And now I'm going to have this curious construction. Whenever the circles have 2 points of intersection, I'm going to draw an edge between those 2 vertices. Now, let me say that mathematically, this maybe looks very complicated, but I want to walk you through a few pictures to kind of show you it's a little bit more intuitive than it sounds. But this construction that we have here, that we have a set of points, we then do this weird idea of we kind of draw these circles based on the nearest neighbors, and then we kind of connect an edge if the circles interact in a certain way. That's what I will call a sphere of influence graph. The intuition here is the more the circles overlap, the closer the points are, and that's why I want to draw edges. So it's almost like saying, if I have a point, I want to know how does that point influence other points? Right, so that's going to be the intuition here. Now let me just say that the very general motivating question is, what can we say about such graphs? So before we worry about any of these crazy mathematical definitions, let's try to actually work through a couple of examples. Let's start with 2 points. And now I want to draw these circles. Remember, I want the closest distance. So here I want to make sure that the circles are going to intersect with the other point. And now notice that these 2 circles intersected at 2 points. So I'm going to draw an edge between these 2. The intuition here is that these circles overlap quite a bit. So that means that they kind of influence each other. Right? So with that, we can try to write down a slightly more complicated example. So let's say that maybe here we have a collection of 5 points. We'll do the same thing. We'll kind of draw these circles, ask what's the closest neighbors to them. We see that the circles overlap quite a bit. So we're going to draw all of these edges. Maybe this graph here looks familiar. This is what's called a path graph. Right? Literally, I'm just kind of walking along a path from one point to another point. Right? Let's try to do another example here. Now let's say I have these 5 points kind of written around in a circle. Again, we'll draw these circles, but notice that there's a lot of overlap here. So that means that these points should really all be kind of connected to each other. So this is what's called a complete graph on 5 vertices. Right, let's maybe do another one here. Let's see, here we have 4 dots, but now let's be a little bit careful. You'll notice that the circles don't really overlap a lot. A couple do, but not all 4 of them do. That's why here I'm only going to have these 2 edges instead of a complete 4 edges. Right? That's what I said before about making sure that the circles overlapped in at least 2 points, because I want to make sure that there really is a lot of influence of one points over the other points. Right? Let's do maybe one more. Here, I've just taken a collection of 25 dots at random. Right? Totally at random, we're going to have these circles, see how much things overlap. And you'll notice something curious here. It's like if I start to take these dots at random, and now try to form the so-called sphere of influence graph, things get kind of clustered together, right? It's almost like saying that there are kind of some groups that they kind of all influence each other, and then other groups, they all kind of influence each other, but they're still going to kind of break off into these cliques or into these smaller groups. That's actually part of a larger behavior that I want to talk about next. So remember, the question is, what can we say about these graphs? In fact, I'm going to ask a more specific question. Which graphs appear as sphere of influence graphs? So if you give me a graph, that is to have a collection of vertices and a collection of edges, when do I know that it appears as a sphere of influence graph? So when do I know that I can do this construction of looking at these circles and how things overlap and then kind of figure out how they're all kind of overlapping? So one proposition you can see, this is just purely from the examples we've worked out. Path graphs are sphere of influence graphs, or hopefully you can kind of see how to do this. Just kind of draw your points in a line. Some complete graphs, at least we saw K5, that's a sphere of influence graph. But again, there's a larger question. What are other examples? So what are other graphs you can possibly say do appear as a sphere of influence graph? There are some conjectures about how many edges you can have with such a graph. Remember what I said earlier about it kind of looks like that these graphs kind of clump off in weird ways, that they aren't necessarily completely continuous, but they might clump off in weird segments. So there's a conjecture by these 2 computer scientists, David Avis and Joe Horton, that says if you have a sphere of influence graph on n vertices, at most you should have 9 times n edges. So you just can't have an arbitrary number of edges, that there's going to be some upper bound. Unfortunately, as far as I know, this is still an open conjecture. The best that people know is this result by Michael Sauce that says at most you're going to have 15 times n edges. So I'm just going to kind of leave that out there to say that these are some open questions to think about. Now, I was really fascinated when I heard that Nate Dean's research group was working on this because I had never heard of these sphere of influence graphs before, and I just wanted to know kind of what were they, but I really wanted to focus more on that first question, right? What kind of graphs appear as sphere of influence graphs? So say that one of the first projects that I did kind of along these lines, I actually worked with Talitha Washington. We actually wrote code for Mathematica, so this is part of the Mathematica demonstrations project, and you can go on your computers now if you want and actually download this. Here is an interactive applet where you can actually go in, you can click the vertices wherever you want, and it'll generate the sphere of influence graphs for you. I am not a great computer programmer, but because I really, really found this project interesting, I just decided just to sit down and just write the code. And so we just ran through lots and lots of examples to get an idea of what was happening. All of this came about just purely because I thought Nate Dean had a really, really interesting project that his group was working on. Let me give you a different problem. I want to go over the concept of rational distance sets. This actually got to start kind of in a different way from a good friend of mine named Garrett Kai Campbell. So he's an African-American mathematician. He actually works in number theory. He works in something called elliptic curves that I'm not going to try to define today. But Garrett Kai and I would see each other at different conferences, and he would just kind of tell me about different things that he was working on. In particular, I want to show a photo here, really, really old photo, back from 20 years ago, which is actually a picture from the CARMS conference when it was held at Purdue University. So Garrett and I were just kind of hanging out, just chatting about things, and he told me that Nate Dean had this interesting question about rational distance sets, and Garrett Kai could answer the question using elliptic curves. Of course, I didn't know what he was talking about. I didn't know what a rational distance set was. I didn't know how it was going to be related to elliptic curves. So I want to try to show you what he talked about and then the result that he came up with. So let's start with the following definition. Just like before, let's say that we have a collection of points. Everything sits in the plane, so we're kind of talking about x, y axis. I will call this a rational distance set if two things happen. Number one, the x and y coordinates should be rational numbers, right? The xi, y should be rational numbers. And the pairwise distances should also be rational numbers. So that is, if I take a look at the distances between any 2 points, that should give me back another rational number. Now, in terms of a picture, the way you can think of this is as follows. So in this case, let's say maybe I have these 3 points. And so now if I have 3 points, I have to take a look at the 3 distances between these, and I need to make sure that each of these 3 blue lines is also a rational number. So that's what I mean by a rational distance set. So let me try to stay a little bit behind what's known before I kind of get into the question that Nate Dean asked. First of all, you could try to ask the question, what happens if you kind of restrict to the coordinates, the x and y coordinates being integers? Then what can you say? Well, Paul Erdős and Norman Anning said back in 1945 that if you have an integer in at least 3, then yes, you can do this. You can actually draw things out so that you have a collection of n points where the pairwise distances are going to be integers. Now, the weird thing is, you can do the quick thing of kind of placing everything on a line. Like, for example, think of the number line that's just the integers, right? Between any 2 integers on the number line, their distance is an integer, right? What's the distance between, say, 2 and 5? Well, that'll just be 3. So I can do this silly thing of, say, just kind of place out the integers on a number line and then just say that their pairwise distances are always going to be integers. So they said, let's do something a little bit more interesting. Let's not place them on a line and ask, can we do this? And they said that, yes, you can always do this in this case. I do recommend that you take a look at the paper. It's something like 2 pages. It's really short. It's really easy. It's a really quick read. If you wanted to see maybe an example when n is equal to 3 to kind of see how this works, the picture that I just showed before about kind of those 3 vertices forming a triangle, that it turns out is an example of a 3, 4, 5 triangle. So if I place maybe one of the vertices at the origin, another one along the x-axis is 3, 0, and another one along going in the y direction at 3, 4, you can check that their pairwise distances give you back a 3, 4, 5 triangle. So that's an example of 3 points that don't lie on a line, such that their pairwise distances are all integers. Now let's not focus on integers so much. Let's try to focus on rational numbers. So as I just said, if you kind of place out the integers on a number line, their pairwise distance are integers. There's nothing to stop me from looking at the rational numbers on a number line. Now notice there that their pairwise distance are rational numbers, right? What's the distance between, say, maybe 1/3 and 2/5, right? Just kind of take the difference there. That's going to be some rational number. If you take a look not just at lines, but even at circles, then you can actually draw a circle in such a way such that you have a rational distance set. I want to go over these last two here in a bit more detail because I have to admit that these two really kind of inspired me to figure out like what's really going on here. In fact, I brought this up with one of my first graduate students. This is a picture here of Kevin Mugo. Stephanie mentioned earlier that I worked at Miami University of Oxford, Ohio with Sumtree. I actually met Kevin, my very first graduate student, when he was a student in Sumtree. He actually was an undergraduate at Otterbein, and so he ended up working at Sumtree, and that's when we first met. We had such a great time that I recruited him to be a grad student of mine some years later. So this is the picture here of his thesis defense. You can kind of see the five of us all kind of standing in the hallway at Purdue University. And then over here on the left, that's when we kind of took him to dinner afterwards. And he's all smiling, probably because he knows that he's done and he doesn't have to worry about me harassing him anymore. But I was so interested in this question with Nate Dean that I told Kevin, you know, there's this statement of you can find infinitely many points on a line that are at rational distance. You can find infinitely many points on a circle that are at rational distance. Why is that true? Can we prove this? So first, let me say that when you're dealing with a line, kind of the idea is that you can take these rational numbers, you can just kind of place them however you want. Like think of any rational number you want, place that on the real line, and you're going to have all of these dots, right? Of course, you're going to have more and more. You're going to have infinitely many dots. But you may remember this result that next to any real number, you can get an arbitrarily close rational number, right? Every real number can be really well approximated by a rational number. That's just a fancy way of saying, or I should say a simple way of saying, that the rationals form a dense set inside of the real numbers. But if you don't feel comfortable with that language, here's kind of a picture to show you what I mean by being dense. Again, I'm placing a dot here at every rational number, and you can see that eventually it's going to fill in the entire space here. So Kevin and I came up with a proof that goes something like this. Let's say that you have an arbitrary line, right? So not just something like the real number line, but maybe something like ax plus by equals c. And we're going to take a look at a special case where a, b, and c are all rational numbers, and a and b will just be satisfying this equation, this expression, a squared plus b squared equals 1. Don't really worry about that too much. But the statement is that if you have this line, that you can actually place in certain rational points on this line, right? That's just a fancy formula here. I would say don't worry about that too much. It's just saying very explicitly that I can place these rational points. And once you do this very clever substitution, you can prove that the distances between them is always a rational number. Right, so again, we just found these really clever formulas to say exactly the picture that you just saw, which means on pretty much any line, you can find a dense rational distance set. Right, hopefully that kind of makes sense because with the rational numbers, it's the same basic idea. So we were starting to think, what about circles? So we have kind of a similar expression that goes as follows. Let's let h, k, and r be rational numbers, and let's consider the circle of radius r centered at the point h comma k, right? So you can write this in terms of the equation that you see here on the screen. So for one thing, for any rational number t, I can start to write down this point here on the circle, and I've written this point in a very specific way such that the distances between points in this form are always rational numbers. Right. Now, I will admit, when Kevin and I proved this, we were really proud of ourselves, only realized that hundreds of people had proved this before us. So it was a little bit frustrating, but still, we were pretty proud of the formulas that we found here. Now, this means, of course, that as we range over rational numbers t and start to plot out the formulas that you see here, we should find a dense subset of the circle. Now, you don't have to take my word for it. What I'm going to do here is I'm going to show you a movie where what I've done here is I've taken those rational numbers t from the previous screen, and I've just taken them at random. So I just told Mathematica, pick them all at random, just kind of plot them out here. So that formula that I just showed you actually does show exactly what you're seeing here on the screen. Hopefully this makes sense, that this collection of rational points forms a rational distance set. But more importantly, it forms a dense rational distance set, right? I can get arbitrarily close to any point that I want on the unit circle by, number one, a point that has rational numbers as its x and y coordinates, and number two, that the distances between pick any 2 points that you want here on the screen, that distance has to be a rational number, right? That's what's really fascinating about all of these formulas here. Now, here's where things get a little bit complicated. So what I've said now is that you could maybe start to draw out things like a line, and now we know that you can form a dense rational distance set for the line. You can draw a circle, and you have a dense rational distance set from the circle. So Stanislaw Ulam asked, what types of shapes could you draw if you wanted to have such a rational distance set? Well, Erdős and Ulam first asked the question, well, what if you focus on having a dense set of points? So you could maybe ask the question, what if you have a dense subset, right? Things like a line or circle. They really wanted to know more generally, what if you tried to have the entire plane, not just the subset, but the entire thing dense? So they asked, can you actually say that any point in the plane, not just lines or circles, but any point can be approximated by a set of points that has to be dense and whose pairwise distances are rational numbers? This is still an open question to this day. But you could try to just restrict to ones where you have things like lines and circles. And so this is a beautiful theorem that came out over the last 15 years or so by Sulimosi and Dezeu that says that really the only times in which you can do this, you have to have lines and circles. You can't really do this like these dense sets if you have any other type of object. I will say that if you wanted to read a really nice history of the subject, Terry Tao just had this on his blog where he really tries to go over this in a lot of detail. There is some kind of high-level mathematics here using algebraic geometry that you might not understand at first, but I would definitely say you should take a look at what he says here. So putting all of this together, Nate Dean really had a rather simple question. So we know that you can draw these lines, you could draw these circles, but other than lines and circles, when can we have an interesting rational distance set? Maybe we can't do infinitely many, but can we still kind of write down something? Well, I want to back up for a minute before I try to go over the answer to that to say that these are kind of the questions that Nate would ask that really inspired a lot of us to say, like, this is really cool. Like, I really want to know the answer to this. I want to show some pictures for a minute to show that Nate also inspired not just the mathematicians, but also really the people that worked in mathematics. So I mentioned earlier that Nate was president of the National Association of Mathematicians, and you probably know that NAM has a banquet that takes place every year at JMM on Friday evening. I have a few pictures here of when Nate was president and he was presiding over the NAM banquet back in 2011. The first photo here is actually a picture of Robert Bozeman, who had just given the dinner address, the Cox Talbot address, and I remember this banquet very fondly because I was there in the room. Here's another picture of Nate just kind of hanging out, just chatting with different people. So this is actually a picture of Nate with Jackie Giles. Jackie was actually on the board when I became president, so I had a wonderful opportunity to work with her as well. But I just want to point this out to say that Nate would just kind of hang out and just chat with people, because that's just the kind of person he was. Here's a picture of Talitha Washington. I have no idea why she's taking the microphone from Nate, but that's typical Talitha. So, you know, just having him around to kind of chat about these things was always great. And really to hit things home a little bit more personally, this year in 2011, I gave the research address, the Claytor Woodard Lecture. I kind of knew about NAM. I don't think that I really knew a whole lot about NAM, but really being here at the conference and actually being invited to speak for the organization made a huge impact on me. It was probably the reason why I agreed to run 5 years later. But really kind of being here at this conference and having Nate give me the award for giving the talk, really, really meant a lot to me. So going back to the math here, remember Nate was trying to ask this question, if you have a rational distance set, what are the types of objects you can write down? Things like lines and circles, but can you do other things? He decided to take a look at the parabola. So let's take a look at this equation here, y equals x squared. And he wanted to know how many points can you draw on a parabola, right, that have x and y coordinates that are rational numbers, and whose pairwise distances are also rational numbers. So he was able to prove that you can always find a collection of 3 points on this parabola, y equals x squared, that forms a rational distance set. In fact, he actually proved that there are infinitely many ways in which you can combine 3 points that forms a rational distance set. I want to come back to my friend Garakai, and this is when I kind of mentioned that I saw him in 2003 at this conference, and he was kind of mentioning these things. Well, this is where Kai was telling me that he knew about this result from Nate Dean, because remember, Nate Dean would always go to CARMS every year. And they told him that, yeah, he had kind of proved this result about having 3 points at a rational distance on a parabola. And he really wanted to know, can you extend that? Why stop at 3? Could you do 4? Could you do 5? Well, Garakai realized that, yes, he could actually do 4 points at a rational distance on the parabola. Now, you might think, okay, that's not really all that interesting. The interesting part is he used elliptic curves to get it all to work out. Now, I'm not going to try to go through all the details of the formulas that are here, and I'm not going to try to go over what is an elliptic curve, but what I do want to say is that he reduced this question to a question of finding other points on other curves. And actually, what's really cool is this is where I got totally fascinated with this project, because I personally work in elliptic curves. I didn't really have a big interest in things like rational distance sets, but it's the fact that I could answer that question using elliptic curves is what really got me interested. When Kai started to take a look at some numbers, he actually realized that he could find one example of 5 points at a rational distance. So these are the numbers that you see here on the screen, but if you can't see, let me try to show you a picture here to kind of show you how this works. Now, just to get an appreciation of how hard this is. Here I have 5 points, the 5 points you see on the screen, and 5 choose 2 is 10. That means these 10 blue lines all have to be rational numbers, right? Their lengths all have to be rational. So it is not hard to find, it's not easy to find 5 points whose coordinates are rational numbers and whose pairwise distances, all 10 of them, are rational numbers. But this is what Garakai found back in 2003. So, of course, I couldn't be showed up, so I really wanted to know, all right, you could use elliptic curves to do these things for parabolas. Could you use elliptic curves to come up with similar answers, but for other types of curves? So fast forward now, a few years later, I was at MSRI UP. This is the MSRI undergraduate program back in 2010. So this is the picture of the group here. And one of the projects I had the group to work on was this idea of rational distance sets. Simply put, the whole set of projects that summer was to focus on applications of elliptic curves. So I just wanted to know, could you use elliptic curves to kind of answer some of these questions? So let me try to show you a little bit of what we were working on before I try to get into the details there. So first, to recap, remember that for the most part, on lines, you can find rational distance sets that have infinitely many points. Remember what I said about these like dense rational distance sets. On circles, you can find rational distance sets with infinitely many points, right? Again, they're going to be dense, but I can still find infinitely many. And based on work of Nadine and Garakai Campbell on parabolas, I could find at least a rational distance set of 4 points. And in fact, there's lots and lots of ways in which I can find such a rational distance set of 4 points. So I had a very simple question going into MSRI UP in 2010. If you take a look at what these 3 have in common, they are all examples of conic sections. More generally, I can write it here using a quadratic equation. So here I have this ax squared plus bxy plus cy squared plus dx plus cy plus f. A, B, C, D, E, F, they're my coefficients. They're all going to be rational numbers. And so I wanted to know, is there a way that I can kind of write a much more general theorem that says something like, for any conic section, can always show that I can find a rational distance set. Well, let me just remind you, in terms of conic sections here, how the classification works based on the first three here at the top of the screen. If you have any equation that defines a conic section in this way, quite literally, a conic section means that I take a cone and I slice it here with a sheet of paper, and then the different ways that I slice this might give me back different types of shapes. So for example, the one that's kind of labeled, the one with the circle, those will give me back lines and parabolas. The two with the circle, those give me back circles and ellipses, and the three there will give me back hyperbolas. You can also think of those three cases in terms of the so-called discriminant of the quadratic polynomial. So in this case, I have to take a look at this b squared minus 4ac. If b squared minus 4ac, this is the discriminant. If that's 0, I would find lines and parabolas. That's like the first case that we looked at. If the discriminant here is negative, those will be circles and ellipses. That'll be like the second case there. And then the third case here would be if the discriminant is positive. So what happens if we have hyperbolas? I kind of thought lines and parabolas, that's kind of what was known classically, and that's kind of what Garakai and Nate had worked on. Circles and ellipses, for the most part, that was also known. But what wasn't known was hyperbolas. So I said, why don't we try to take a look at that case and see what happens. So summer 2010, I had 3 undergraduates, Megan Lee, Sean Sosi, and Literary Resta, who actually worked on this simple question of, let's take a look at any hyperbola. We'll write it this simple way of axy plus bx plus cy equals d. Again, a, b, c, and d are all rational numbers. I'm asking the question, can I form a rational distance set on any hyperbola in this form? What we proved is the answer is yes if our elliptic curve has a certain property. For those that know about elliptic curves, I really want to say that my elliptic curve has positive rank. I don't really want to spend time defining all of that for the talk today. But let me just say that we got some very similar nasty formulas, just like what Garakai had, but they're very explicit. So what it says is if you give me back an elliptic curve in this form, this E sub d, where the d here kind of depends upon the hyperbola, as long as I can find certain rational points, capital X, capital Y, I can translate them into these 4 points on a hyperbola. Again, I don't want to worry about kind of explaining all the different formulas here, but the point is we were really inspired by what Nadine and Garakai had. We just looked at their formulas and said we wanted to do something similar. So let me pause for a minute. Let me just kind of show you some of the pictures here so you can kind of see what we did. So here, let me take a look at this hyperbola, y equals negative 12 over x. And just one of the byproducts of the formula is that if we draw the hyperbola in this way, we have these 4 points. Remember, 4 choose 2 is 6. So here I need to make sure that these 6 blue lines all have rational distances. And that's what you can do just based on the formulas here. So simply put, for any hyperbola, we can always do this. We can always write down these 4 points where we get back a property like this. So we actually felt pretty good that summer that, we were definitely making progress in terms of understanding these rational distance sets. So what I want to do is try to end up here by maybe stating some open questions in the spirit of the way that Nadine would do things. He'd always want to give you some open questions to some things to kind of whet your appetite mathematically. I do want to say, just to kind of finish off the story with Garakai Campbell, Garakai was a number theorist. He definitely worked on things. He and I published papers together. He's a very good friend. The really cool thing is that all of this kind of wound up in a nice circle when I became president of NAM and Garakai Campbell was provost at Morehouse College. This is a picture now of the NAM banquet back in 2017 when it was in Atlanta. And it was just really crazy that he and I had known each other for like 15 years. We had worked on all these different projects together. And now here we were in a totally different life, where here I was president of this organization where Nadine had inspired me. And here it was that he was provost, and he was also able to kind of be there to support me in all of this. So this is actually one of my favorite pictures. So just kind of thinking that all of this just kind of became full circle about 5 years ago or so. And also along these lines, I was able to do an RUF with Nadine back in 2012. So remember I mentioned that the RUF is kind of like an RU for faculty in which you actually get to do research with other faculty. I have done a lot of research projects with undergraduates, but this summer was one of the first times I had done research projects with other faculty members. You can see here that there are kind of 4 of us sitting on the front row. I'm over at the very Left in the white shirt, Stefan Garcia, who's now my colleague at Pomona College. Leslie Hogman, who was at Iowa State University. She's retired now. And then you see Nadine, who's on our very right there in the green shirt. Now, yes, everyone in the back are kind of faculty that we were all doing research with, but I have to admit, the most fun I had this summer was hanging out in an office with Nadine, just chatting about math problems. Because I don't really know if the other faculty kind of knew this, but a lot of times we would just kind of lock the door and we would just go to the chalkboard and just start talking about random crazy problems and really crazy results. So I just had the time of my life being an office mate with Nate. So these are kind of some of the questions now that Nate, I think, has at least inspired me to think about. And now I'm hoping that I'll inspire you to think about these. One of the first questions is, which graphs appear as sphere of influence graphs? Remember that you have this construction of a sphere of influence graph. You kind of start with your vertices, then you kind of construct the edges in this way, but which graphs appear like this? So you can kind of think of maybe some of your favorite graphs, things like a star graph, a cycle graph, a wheel graph, caterpillars, trees. Those of you that know about graph theory know that there's a lot of different graphs out there. Well, which of those appears sphere of influence graphs? And how do you actually construct the sphere of influence graphs so that you would actually get back these different examples? If G is a sphere of influence graph with n vertices, must it have at most 9 times n edges? So one thing you could do is you could just say, okay, let me start with n vertices, maybe just pick n kind of at random, and then now construct the sphere of influence graph. And now ask, how many edges do we have in such a graph? Remember how I kind of mentioned before that it isn't going to be super connected because kind of things are going to break up into these different clumps. That's kind of what this is getting at here. So the question is, at most, how many edges might you have? Moving on to rational distance sets, you can ask, does the plane contain a dense set of points whose distances are all rational numbers? Right, so this is what's called the Erdős-Ullmann problem. This question of not just saying that things like you have a rational distance set that's dense on the line or dense on the circle. What if you tried to do the entire plane? So if you have the entire plane, can you form this rational distance set where you get arbitrarily close to any rational point and the pairwise distances are all rational numbers? Right? Again, this is an open problem. Are there infinitely many rational distance sets consisting of 5 rational points on the parabola? Right, I mentioned that Garrikai proved that you can always find lots and lots of rational distance sets of 4 points on the parabola. He only found one example of 5 points. So a question that Kai has asked me over the years is, can you find infinitely many for 5 points? I mentioned here about this conic section, and remember that you can kind of break this up into different cases by looking at the discriminant. But really, we were only looking at very specific cases. Things like if you have a parabola, that just corresponds to when the discriminant is 0. I've only looked at a very specific case here. What if this y is equal to x squared? But what if you have an arbitrary parabola? Maybe something like y is equal to 5x squared. In that case, can you still always find a rational distance set of at least 4 points? Right? Again, it's an open question. I don't think that anyone's really worked on this. And the last thing I'll leave you with is, are there shapes other than conic sections where we can place these rational distance sets? Right? I've talked about lines, about circles, about parabolas, about hyperbolas. Those are all conic sections, but what if I move to other types of objects? Other types of things that I can kind of draw. Can I do the same trick? Can I find all of these? Well, these are definitely things that I am still actively thinking about. But I want to end here by saying, yeah, all of this is related to the concept of distance, kind of looking at like things like distances between points. But for me, it really comes down to, say, the distance that you might have in the relationship with someone. I can definitely say that Nadine is someone who really meant a lot to me. He definitely was a huge influence, not only on the research that I've done, but kind of from the way that I've interacted with students. And even now, say in terms of the work that I do with helping to diversify the mathematical community. A lot of this really came from how close I felt to Nate and just like learning about his passion with things. So with that, I do want to say, not only does distance mean so much when someone means so little, when someone means so much, but happy birthday, Nadine. So thank you. Thanks for your time. Right, I'll try to repeat the question. Thanks very much for that. The question comes down to sphere of influence graphs and how it really relates to, I guess, like life and social structures and what have you. There's a lot of impact there. I can't say that I know what all of the impact is, but I do know that a lot of this does have lots and lots of applications to, well, just to sociology. One thing I didn't say about these graphs is that you can play around with the definitions a little bit. There is some question of things like whether you have what's called an open sphere of influence graph, that's the definition I gave here, versus a closed sphere of influence graph. And that comes down to how much overlap the circles have. The way that these spheres of influence graphs are defined, the way I taught them today, really says that there should be a significant amount of overlap between them. But that's really where the whole concept of influence does come in. I would be very interested to see exactly how this would be applied, let's say if you were perhaps in the humanities, really if you were thinking of what are different metrics you can use to talk about distances between people, between groups, and what have you. I know that Nadine himself was very interested more in the visualization of all of this. So there's this theorem that says that if you have a sphere of influence graph, you can always place the vertices on an integer lattice to then take a look at the distances there. That's part of the reason why Talitha and I wrote the code, because we kind of knew that we were able to visualize it. But it is such a simple concept that I think a lot of people in other areas can use this and use it to great extent. I personally don't know. I haven't really worked in this area enough, but I would love to see applications to see, like, can you measure things like social networks or Facebook or Twitter and just how much people are connected? It's such a simple concept that I think you could really get a lot of mileage out of it. Yeah.
Any other questions? Yes, over here.
Uh-huh. Yeah, that's a good question. The question is, when looking at rational distance sets, you can ask about how many dimensions you have. So like one dimension, that's kind of the line. 2 dimensions is what we talked about here. So what about 3 dimensions and higher? I know that there is some work done on that. I don't quite know which types of objects you can get, like whether you might have a rational distance set that's like the sphere and the plane, and then you can do other things. By using the formulas, you can definitely do something very similar. But honestly, I don't know. I don't know what results are out there about that. So I think that's an excellent question. Yeah, that's definitely along the spirit of what Nadine would ask too. Yeah.
Maybe one more question? Yes, over on the side here.
So the question is, when you're dealing with sphere of influence graphs, I asked the question, what types of graphs can you get? And you're asking, what if you sort of focus on the number of vertices and maybe kind of go from there example after example? I actually don't know. That is a very good question. I have to admit, I did try to do some looking into like this exact question, what are the types of graphs that you can come up with? And I didn't really find a whole lot. So I would love to know the answer to that, but I wish I could tell you. I just don't know.